Hi there. We're going to do a derivation about the harmonic oscillator. And we'll go over to the paper view here. The harmonic oscillator. And this could be, for example, that you have a atom. Let's say that it's oxygen. This might be on the surface of a catalyst. So there's a chemical bond, and then there's a surface. And then since there's some force constant here with the bond, that atom might be vibrating back and forth, right? Something like that. And so we've introduced a spring into the system. And you can just think about a spring a little bit. We have a spring here. You have a spring. You can compress it, whoop, go like that. You can stretch it. And let's see, we'll put the pen back together. And some springs, over a certain range, they act as a linear spring. And that means that the force that you need to displace the spring simply depends on the distance. So we have some constant and we have a displacement, the distance. And always the force is opposite to the displacement, right? So if you squeeze the spring in, the spring is pressing out. Or if you try to stretch a spring, the spring is pulling back. So we need a negative sign here. So it's the opposite of a force constant times the displacement. This is known as Hooke's law. So in this system, we're going to have a linear spring, and the system is going to be subject to Newton's law, Newton's second law. Here, force is equal to mass times acceleration. And so we have the mass of the atom, we have the force constant of the bond, we have the position, and we have the acceleration. And let's just think about this a little bit. We have a position. This could be x. You could have a velocity, dx dt, right? So the change in the position is the velocity v, and we could have an acceleration, which is the second derivative of the position, or the first derivative of the velocity, and that's a, right? So what we're really saying with Newton's second law is that force is equal to mass times the second derivative of the position. And we need dt squared. And so if we equate these two, force from the spring is equal to force from Newton. This means that opposite of kx is going to be equal to ma equal to m d squared x over dt squared. And I think that's an interesting equation. And one of the things is that it looks like x is proportional to its own second derivative, right? So we have x equal to some constants and its own second derivative. Of course, this is saying that x is a function of time, since we're able to take the second derivative with respect to time of x. So x must be a function of time. And this is a wave equation. This is something that we could solve and hopefully learn something about the behavior of our atom with time. So let's take a time-varying function. And if you think about this a little bit, you could think, what functions do we know that are proportional to their own second derivative? Well, of course, sine and cosine are proportional to their own second derivative. So why don't we start by just taking some arbitrary sine function, We can have an amplitude of that function. We'll call that A. And we'll multiply that by some kind of a frequency and the time. Right? So we have a time varying function. We have a certain frequency of oscillation. We have a constant 2 pi that's in there. And that's our time varying function. So if we take the first derivative, this is going to be A. You remember your rules about how to take the derivative of a sine function. This is going to be A times 2 pi nu times cosine 2 pi nu t. And then we can take the second derivative. So this is the velocity. It's an x, it's a cursive x. And we take the derivative of the cosine, that's the opposite of the sine, so we're going to get a minus sign in there. And this will be the minus a 2 pi nu squared sine 2 pi nu t. We can take this equation and substitute that into our original equation here, right? So if we do that, we're going to get the opposite of k times x as a function of t is equal to mass times the second derivative of x with respect to time. So this will be the opposite of k a sine 2 pi nu t. And then this will be m times what we just saw. So this will be opposite of a 2 pi nu squared sine 2 pi nu t. Out of this, we can simplify. And we find out that the frequency is equal to 1 over 2 pi times k over m to the 1/2. That's very nice, right? You see that the sign on this side cancels with the sign on this side, and a cancels with a, and this cancels with this, and you solve that for the frequency. You can pull the frequency out, you end up getting the square root, and overall, you find that the frequency of oscillation is going to depend on the force constant of the bond, the chemical bond or of the spring, and the mass of the atom. This is a very fundamental relationship. You could say, for example, that you have some single bonds. Hydrogen fluoride. You could have hydrogen chloride. And in this case, this tells you, if it's a single bond, the bond strength is probably the same. So the force constant is going to be about the same. And the thing you've done is to change the masses that are involved. And because you change the mass, you've changed the frequency. So this says, for example, that since molecules have unique combinations of masses and bond strengths, that we will have unique vibrational frequencies that are characteristic of the different compounds that are involved. And a lot of analytical chemistry is based on these unique frequencies that you have for different bonds. Now, you remember in the first problem that we had one free end. So we had a mass, we had a bond, and then this mass is oscillating back and forth. It's the harmonic oscillator. And this end is fixed. And of course, that's not true when you have hydrogen fluoride and hydrogen chloride, because maybe this is moving back and forth And maybe this is moving back and forth. This is going to be moving quite a bit. This will be moving a little bit. And of course, oscillating around the center of mass of the molecule, which is going to be over towards the heavy end, the fluorine. And in order to account for this, we can introduce something called the reduced mass. This is going to be mu. And in the case that we have two masses, M1 and M2, the reduced mass is going to be M1 times M2 divided by M1 plus M2. And so then we can put that into our formula and find that the frequency is 1 over 2 pi times k, the force constant, divided by mu, the reduced mass, to the 1/2 power. And that's the introduction to the harmonic oscillator. Thank you very much.